This is the first lecture of the Differential Topology course of the PhD program of Universidade Federal Fluminense in Brazil. The main goal of this course is introducing the students to the fundamental ideas of transversality and intersection theory. For instance, we are going to see and prove that the Poincaré-Hopf theorem and the Ledger-Hopf theorem that relate global topological information of manifolds with local properties. Besides that, we are going to see many other properties, like, for instance, the Whitney embedding theorem or properties of fiber bundles. What is going to be, or what are going to be the books that we are going to follow in this course? Since our students have not had a lot of contact with topics related to differential topology, the idea in the first lectures is following the Guillemin-Pollack book, Differential Topology. Even if this book is for undergraduate students, it introduces very nicely the main concepts of this course. And then once we know the main ideas, we will switch mainly to Hirsch's book, Differential Topology, in which, let's say, more analytic, more advanced tools are introduced. In the first lectures, we are going to introduce elementary ideas about differentiable manifolds. In a first moment, we will deal with embedded manifolds in Euclidean spaces, and then we will use the properties of these manifolds to introduce abstract manifolds, which are going to be mostly the object that we are going to deal with in this course, together, of course, with differentiable mappings between these differentiable manifolds. We will see in this lecture the definition of embedded manifold in an Euclidean space, together with some examples. The fundamental example of a manifold is R to the power n, or any open subset of R to the power n, whereas the fundamental example of submanifold is a linear subspace of R to the power n, or an open subset of such linear subspace. The idea is that manifolds are going to be built by pasting this kind of local data. Of course, we are going to allow this local data to be modified via diffeomorphism, right? Now, let us see some examples. We didn't define so far what a manifold is or what the dimension of a manifold is. But in order to develop our intuition, let us introduce a few examples of surfaces. This picture has been borrowed from the Guillemin-Pollack book about differential topology. These are going to be examples of manifolds of dimension 2, in other words, surfaces. And we can see that locally at any point, they look all the same. On the downside, downstairs, we have an example of something that it's not going to be for us a manifold. It can be considered as a variety, but it's not a manifold because it has a special point. This point clearly has a different nature from the others locally, so it's not going to be a manifold. We are going to assume that we know what a CR map from an open set of R to the power n to R to the power m is. It's going to be a map whose components are functions that are R times differentiable and with continuous derivatives. It is possible to generalize this definition for maps that are defined now in any subset of R to the power n. And what we are going to do in order to extend this definition is using an extension approach. What do I mean by that? We say that if f is differentiable of class CR if for any point x in our set, we can extend this map small f to a map big F that is defined in a neighborhood of X now in R to the power n, in other words, in our ambient space, and such that these two maps, big F and small f, actually coincide in our set X. That's going to be the definition. That's what it is written there. We need that for any point there exists an open neighborhood U of X in the ambient space and a zero map big F from U now being an open set of R to the power n to R to the power m, such that these two F's, the big and the small ones, coincide in the intersection of the common domains of definition. In other words, or the common sets of definition. In other words, X intersection U. We just saw how to extend the definition of differentiable map to any subset of an Euclidean space. Now let's give the definition of a submanifold of an Euclidean space of dimension k. So consider a subset X to the ambient space R to the power big N, and we say that as X is going to be a submanifold of dimension k. And here let's point out that all the definitions are local, so it's going to be something that we have to check out at any point of our set X. If given any point, there exists an open subset of R to the power k and a map phi sub b from U to X intersection B such that the following properties hold. The first one is that V is an open neighborhood of X in the ambient space. That actually is going to guarantee that this set is actually an open neighborhood of X with the induced topology. Moreover, we are going to require two further properties because so far what this says, if we are just actually considering the first property, is that we have a map from an open set of R to the power k to an open subset of X. Indeed, an open neighborhood of our point small x. But we don't want just that. We want to identify, if possible, these two sets. So in order to do that, we are going to require two further properties. The first one is that phi is going to be an immersion of the proper differentiable class, CR. If we are considering a CR submanifold, it has to be a CR immersion, okay? And the last one is that this phi is going to be a homomorphism. We will discuss later, I think, this condition. With all these properties, we say that X is an embedded manifold in an Euclidean space. The last one is to avoid the possibility that actually when we are giving to X the topology that is induced by the topology of U and the fact that this map is a bijection, we obtain something that is different than the topology of X as a subspace. That can happen, and in order to avoid this possibility, we require this map to be a homomorphism. The inverse of the map phi is going to be called a local chart by definition. So local charts are the inverses of parametrizations. And we are going to have also maps of change of parameter. You have to realize that the phi that we considered in the definition is not unique. So it is perfectly possible that a neighborhood of a point in our submanifold is parameterized in different ways. For instance, using the parametrizations phi sub b and phi sub w. Because of that, we are going to have maps of change of parameters or coordinate changes that associate the parameter that actually parameterizes a certain point to another parameter that parameterizes the same point for a different parameterization. And these maps, as a consequence of our conditions, are going to be CR if our manifold is CR. Now we're going to consider an example of submanifold. Indeed, a submanifold of R2 of the plane. And our example is going to be very simple. It's going to be just the circle S1, the points of the plane that are at distance 1 from the origin. So here we have the definition of the circle as a subset of the plane, and we have to consider these parameterizations that are going actually to show that our circle is submanifold. So we consider the points of the plane whose x-coordinate is positive. And for these points, for the points of that set P intersection with the circle, we have a parameterization. Because the idea is actually quite simple. Oh, sorry. If we consider the circle and the points whose first coordinate is positive, for such points, the height of the point, the second coordinate, actually parameterizes the point. If we fix the second coordinate, in general, we have 2 points in the circle. But if we just restrict ourselves to the points whose x-coordinate is positive, then for every possible height, there is just 1 point of the circle. This is going to give to us a parameterization by the second coordinate. And obviously here, since x has to be positive, the first coordinate is the positive square root of 1 minus y squared. We can consider obviously other local charts, other parameterizations, because not all the points of the circle have the x-coordinate being positive, so we need obviously more parameterizations. We consider, for instance, this one, w. So we are going to parameterize the points of the circle whose second coordinate is positive. And again, by using a similar idea, we can actually parameterize them by the first coordinate. Again, since we are considering just the points of the circle whose second coordinate y is positive, the square root that we have to consider over here is still positive. Of course, if we consider here a negative x, then we should consider here the negative square root. And if we consider here the points with second coordinates negative, here we have to consider to the negative square root. Now, there are points that have been parameterized twice, right? Because if we make a picture of the circle, the points that satisfy that x is positive and y is positive have been parameterized twice. Okay, so the points more or less over here have been parameterized twice. And so there is a map of chains of parameter corresponding to these points. And this map is the composition of the first parameterization with the inverse of the second. If we apply the first parameterization to y, we are going to obtain this formula, yeah? But if we apply the inverse of the second parameterization, let's see over here that the inverse is going to send a point into its first coordinates. So here, the result of applying the inverse of phi sub w to this expression is going to be just the square root, the positive square root of 1 minus y squared. Okay, and where is that map defined? It's going to be defined in the interval 0, 1. You can check that out. And because of that, this map over here is actually a diffeomorphism. This map defines a diffeomorphism between the interval 0, 1, the open interval, and itself. And this diffeomorphism is even real analytic, okay? Because even if we have here a square root, since the argument of the square root is never actually equal to 0, because this is 0 just for y equal 1 and minus 1, and those values do not belong to the interval, we are going to have that this change of coordinates is actually a real analytic, which is not surprising because these maps over here are real analytic. So in this way, and obviously we have to consider more local charts because those two charts do not cover the whole circle, but the calculations are the same. We actually prove that the circle is a real analytic submanifold of the plane. In the first lectures, we are reviewing some concepts about differentiable manifolds. The first lecture was devoted to embedded submanifolds of Euclidean space, whereas in the next one, we are going finally to introduce the definition of an extra manifold. Thank you for your attention.